Recall from last time that the basic tenet of simple harmonic motion is that whenever F equals negative kx, wherever this is the net force acting to restore a mass m to an equilibrium position, then if you take a mass and release it from rest at x equals a, that mass will undergo simple harmonic motion with this function, describing the position of the object as a function of time. X of t equals a cosine of omega t plus theta 0, where omega is the square root of k over m, k from here, m being the mass of the object being restored to equilibrium. We've already seen the circular model of this situation, and we'll be referring to it repeatedly. Here's a typical situation. We have a spring with two 1 kilogram masses exerting a force of 19.6 newtons, or on which a force of 19.6 newtons is exerted by gravity. The spring must therefore exert an equal and opposite force to support that weight. We notice that the spring is displaced, stretched to a point where the top of the top weight is at a distance, at a position of 30.4 centimeters as measured on a vertical scale with a meter stick. When we add another kilogram so that we have 29.4 newtons acting downward, we note that the spring has stretched to support the additional weight. The more the spring stretches, the greater the force tending to restore it, an F equals negative kx type situation. At this point, the position of the top weight is 33.6 centimeters. That's a change here of 3.2 centimeters. The change in the force, the difference in the two forces exerted by the spring, is going to be k times the difference in the two positions of the spring. So that the difference of the forces, difference between the 29.4 and 19.6 newtons is 9.8 newtons. That's going to equal k times the difference in positions, the 3.2 centimeters. And we solve this to get k equals 3.6 times 10 to the second newtons per meter. From this, we're going to be able to predict the angular frequency of the situation. Okay, from k equals 3.6 times 10 to the second newtons per meter, mass of 3 kilograms, we predict omega, we predict the period. And of course, we use the circular model. Remember, omega is the number of radians per second. T is the time it takes to go through the 2 pi radians of the reference circle. We can then set the system in vibration and time a number of oscillations to observe the period and see if it agrees with what we predict, and we'll find that our prediction is very good here. Now, if you're at home, you can take your spring and suspend a 2 or 3 liter pop bottle filled with water and get a pretty good approximation to this situation. The pop bottle weighs a little bit, I think about 40 grams or something like that. You can measure that and take that into account. Okay, but the idea here is to measure the force constant with some known masses and then predict omega and use that to predict the period, then observe the period and compare.